Okay, welcome back. What I want to look at is logic gates, and I'm hoping that you'll find this information useful. Now, logic gates. Now, what we are looking at here is the logic gates that goes to make up an integrated circuit, and you can often buy these in little packages. Now, what comes to mind is the 741 family of integrated circuits. Okay. Now here we have logic and gate. Symbol, that's your symbol and function. Now here you have two inputs, A and B, and output is Q. Now two input and digital logic gate. Okay. Now what actually happens here is that we've then produced a truth table, and we have input A, input B. Now bear in mind, this is not how I would normally write it. I would normally put the A this side and the B that side, but as someone seems to have produced this the other way, it doesn't really matter which way around that is reading. Okay, the main thing is that the table will function whether A is in this column or whether B is in this column. Okay, so here we have, assuming that we have 0 input here, 0 input here, then the output to Q will be 0. Now let's change that a little bit more. If we put 0 at B and we put a logic 1 at A, then the output to Q will still be 0. Now again, let's change that around. We put a 1 on B, a 0 on A, and the output will still be 0. Now we have applied 1 to B and 1 to A. So here and here we have now logic state of 1. That gives us a logic output 1. That means that to get any output from this and function from this AND gate, both logics input must be at logic 1. Okay. Now draw the diagrams out for yourselves. Make yourself familiar with the type of symbols that's been used. Get used to the truth table, because these truth tables then appears in what we call Boolean algebra, and you will need to understand the truth tables in order to simplify the Boolean expressions. Okay. And here we are already, you can see here we're talking about Boolean already expressions, Q equals A and B. Okay, read as A and B gives Q. And what they're trying to say here is that you must have a logic 1 at both A and B to get a logic output of 1. Now Boolean expressions Q equals A and B. Now we will look at that in more detail in due course, but not right now. And I think I may have done a little bit on this already in one of the videos, and I think it does say Boolean expressions. So I will look at that and tie that into this, and you'll find that it should actually work quite well. And here we have the logic OR gate, symbol greater than or equal to 1. Now here, truth table, again B and A, or A and B if you prefer, just a matter of preference. Sorry about that, I went off camera then, 1 second. Now, what state must exist in order to get a logic output 1? Now you see that if A and B is at 0, you get a 0 output. But if A has a logic 1 and B has a logic 0, you will get a logic 1 output. If B has a logic 1 and A has a logic not, you will get a logic 1 output. And if B and A both has logic 1s at their input, you will get a logic 1 output. Okay, that's what the logic OR gate does. Now, Boolean expression Q equals A or B. And read as A or B gives Q. Okay? And here we're looking at what's called the inverting gate, which is a NOT gate. Or, well, in this case it is not a NOT gate, but it is a NAND gate. But I expect we'll look at the NOT gate a little later on. But inverting logic gates. Now, the logic NAND gate symbol, as you can see, but the difference here between your AND gate and your NAND gate is this little circle here. That is, you can call this your inverter if you like. Okay. So what that does is input NOT or NOT will give you a 1. Input to A or B, if B has a NOT input and A has a 1 input, then you get a 1 output. If B has a 1 input and A has a 0 input, you'll get a 1 output. But where A and B has a logic 1 input, then the output is 0. Now, Boolean expression Q equals A and B. Read as A and B gives not Q. Okay, so what that's just trying to say that the output to Q is inverted. So whatever it is, it will be the inverse of Q. But keep in mind the truth table. Write the truth tables out, because these will tell you the functions of each gate. And believe me when I tell you that when you begin to link these gates together, you can almost produce magic, because the function of this gate can make a given circuit do certain things and operate in manners that some of you may not have even tried yet. But I can tell you this, that once you get into these logic gate systems, they're quite a joy to work with. Now what I'm looking at now is the logic NOR gate. Well, basically not OR. And you remember that we just looked at the OR gate, okay? But this is not the inverted version of that. So here, input B and A, or A and B. If the inputs at A and B is 0, 0, then you get a 1. If the inputs at A is 1 and the input at B is 0, then you'll get 0 output. If the input at B is 1 and the input at A is 0, then you'll get a 0 output. If both A and B are at logic 1, then the output will be 0. Now again, the Boolean expression here is Q equals A or B. Read as A or B gives not Q. Again, similarly, you would have read that earlier at another stage. Okay, but there's a link between them. But remember that this is the logic NOR gate. Don't get confused with the previous mentioned work. Read the information, write it out for yourself, draw out the truth tables, get familiar with what you've been asked. Now, exclusive logic gates. Now, the logic exclusive OR gate, EX-R, or or I should say. Now again, this that's your symbol. Okay, keep it in mind. Draw it out. Become familiar with it. Know which gates you're talking about, because the truth table for each one is different. Okay, so here we have input at A and B is 0. You get a 0 out. If the input at A is 1 and the input at B is 0, then you get a 1. If the input at B is 1 and the input at A is 0, then you'll still get a 1. But if you have an input 1 at A and input 1 at B, you will get a 0 output. Now the Boolean expression here is Q equals A, B. Now it's okay, I'm just pausing a little bit because when I did some expressions the other day, there should be a bar that I'm thinking of, but don't let me confuse you. We'll just deal with it as it stands at this moment in time. I'm thinking of the not a bar over version. It's okay. I'm just getting ahead of myself. Excuse me. Right now, read as A or B, but not both, gives Q. Okay. So simply, if you have a 1 at A or 1 at B, then you'll get a 1 out. But if you have both at logic 1, in this case, you will get 0 output. And here we have the logic exclusive NOR gate. Logic exclusive NOR gate. Symbol again, almost identical to the exclusive OR, but not quite. What's the difference? The difference here is your little inverter, and that's what makes a difference. Now look at the truth table. If A and B is at 0, you get a 1 output. If A is at 1 and B is at 0, you will get a 0 output. If B is at 1 and A is at 0, is at 0, yes, you'll get a 0 output. But if A is at 1 and B is at 1, then you will get a 1 output. Okay, now Boolean expression Q equals A, B. Read if A and B the same gives Q. But again, that little bar function which should be across one of these here, I believe, is still in my mind. So, but I will take this as read at this moment in time, but do a little additional research on logic gates for yourself, just to make sure that this one, the symbols are still up to date. 2, has there been any changes in regards to symbols? And 3, for your own edification, learning that means. Okay. Now here we're looking at single input logic gates, the hex buffer. Now don't be put off by this. Hexadecimal figures is to the base 10, to the base 16. Okay. And you're not doing hexadecimal just yet, but you will do hexadecimal to the base 16 in regards to binary logic. Now, those binary logic will go into hexadecimal, and they will also look at octal. values, but at this point in time we're not dealing with those. All we're looking at is purely the logic gates that gives us certain logic functions in regards to these possible hex and octal functions. Okay. Now here we are. Symbol, Boolean expression. And here you can call this just a NOT gate. Okay, I will refer to it as a NOT gate because simply you get in what you put out basically. But this will be an inverted NOT gate. So here we have the basic NOT gate. So you get in what you put out. Expression Q equals A. Right? But here, as we go on now and we put in an inverter into our NOT gate, this now becomes the NOT gate inverter. So here, that's our little inverter from this stage. Okay, so we've put this here, which does not exist here. Okay, and that makes a difference. Now that changes our truth table completely. And if you have a NOT in, you'll get a 1 out. And if you have a 1 in, you're going to get a NOT out. Okay, so again here you can see you can modify these and adjust the truth tables with combination of other logic gates to create quite a complex system. Now, Boolean expression Q equals not A or A, read as inverse of A gives Q. Okay, and that's just for a simplified version of that. So sorry about that. Now I probably should have made this bigger, I think. The operation of the above digital logic gates and the, let me just go back, make sure I can get it all in, and the Boolean expressions can be summarized into a single truth table as shown below. Now this truth table shows the relationship between each output of the main digital logic gates for each possible input combination. Okay. Now, digital logic gate truth table summary. The following logic gates truth table compares the logical function of the two input logic gates, detailed above. Now, all I am saying here now is that, let me just move in. Sorry, let me just pan out first. Make sure you get it all in, and then let's go into your truth table. Okay. Now, we're looking at the two inputs here, whatever these inputs may be. And all you can see here is that for an AND function, you will only get a 1 output when you have a 1 input at A and a 1 input at B. That's the function here. Now, what this then says here is that we're looking at the NAND gate, and you will get a 1 output if you have a NOT and a NOT at both A and B at the input. You'll get a 1 output for the NAND gate if you have a 1 or a 0 input in respect of the two inputs. If you have a 1 at A and a NOT at B in the input, you'll get a 1 out. But for the NAND gate, if you have both a 1 at A and a 1 at B, you'll get a 0 out. Now again, for the OR gate, you'll get a NOT out for a NOT and a NOT in. You'll get a 1 out for a NOT and a 1 in. You'll get another 1 out for a 1 and a NOT in. And I'm just using the term in, taking these A and B as the inputs. Okay, and you can see that. Now the NOR gate again gives you, bearing in mind that these are two inputs, A and B, NOT and a NOT. For the NOR gate, you'll get a 1 out. But For any other functions, they will all be 0. And here you have the exclusive OR function. Okay, and again you can see here that you'll get a 1 out when you only have a 0 or a 1 at either A or B, and you'll get a 0 out if they're both the same inputs. Okay, and again that is reversed for the exclusive NOR function. Now again, write out your truth tables. Get familiar with the input for each gate. So I'm just panning back a bit, just to make sure we can get it all in. Okay. I'm sure I just feel like I'm sitting sideways at times, looking at this. Okay. And here we have truth table output for single input gates, NOT, etc. And that is simple enough to understand. Okay. Now, what I want to look at here is what we deal with something called pull-up, pull-down resistors. Now, one final point to remember when connecting together digital logic gates, to produce logic circuits, any unused input to the gate must be connected directly to either a logic level 1 or a logic level 0. Yeah. Okay. My apologies for that. Goodness me. Sorry about that. Wow. These things don't have to happen unexpectedly. Sorry, right. Let me just recap that. To produce logic circuits, any unused inputs to the gate must be connected directly to either a logic level 1 or a logic level 0 by means of a suitable pull-up or pull-down resistor. For example, 1 kilo ohm resistor to produce a fixed logic signal. This will prevent the unused input to the gate from floating. Now, what we mean by floating is that if it's not tied down to either a logic 0 or logic 1, it causes interruptions to the binary logic system of the gates themselves, and it causes the gates to fluctuate between a 0, 1 and a 0 and 0 itself. This can cause the gates to be tripping or switching when you don't actually want them to be switching. So that will not be in your best interest. So about, okay, thank you, let me pick up where I am. From floating about and producing false switching of the gate and circuit. You need to minimize that completely in any logic system that you are working with. And this is how it would look like. Okay, you would have your 5 volts here. Your own, now please excuse the old-fashioned resistor model. I know that these should now be modern square, etc. resistors, but just accept my old-fashioned methods for now. Okay, that would be your rail, your positive rail. Okay, you have a logic 1 here. That the resistor is to maintain any excessive load to your gate, which does not cause it any excess current to flow. the resistor will take up that if need be. Now that's your pull-up resistor. These will be your input that will trigger your gate. Yeah. Now here we now pull down resistor against approximately the same value, and you turn it down to ground, to 0 volts. So somewhere between your positive 5 volts and you will have a ground. Okay. Now normally we can build this on a breadboard, and you can actually see your positive rail and your negative rail, or negative rail, which would be your zero rail in that sense, if you wish. Okay. But bear in mind, that's what your pull-up resistor. So these floating gates, if they're not being used, will be tied down. Now we can assume this to be a free input AND function and a free input NOR gate. So one of these inputs, because we're only dealing with 2 inputs, the other input has to be tied down to either positive or 0. It ensures that when your system switches, it switches positively and does not fluctuate between positive and negative, or binary 1 and binary 0. It gives you a clean switching action. Okay. Okay, I think that will be it for now. I hope you will find this useful. Okay. And let me just pull back a little bit so we can make sure we get it all in. Okay. And I believe we have. Okay, thank you for your time. Have a good day. Bye-bye.